All right, so hello everybody. So my name is Aimane Najmeddine, and I'm an associate research scholar at Princeton University, working with Professor Moini, who's in the back today. So there was one question earlier today about the interface and how to model that. And there were a couple of other presentations today which mentioned something about the interface and how to really look into it in terms of these composite multi-material systems, but also just in general in 3D printing of layered semi-system materials. And so today's talk, we'll be talking exactly just about that. So the person who asked the question, you're in for a treat. So we'll be talking today about a numerical model that we've developed in our lab to look at the crack propagation in multi-material, hard, soft, and hard architected materials. And so this is kind of like a prelude to what you would have to use if you had multi-material printing, which a lot of these people today have talked about. And so I'll start off by talking a little bit about some motivation behind why we even want to work on architected materials. And the reason for that is that because we find this very ubiquitous in nature. And so nature has this ability to actually work on developing materials or natural organisms for the sake of continuity, so species continuity. In this case right here, we're talking about nacre, which is a very common material that you can find, for example, in the outer layer of oysters, or just kind of oyster-like materials. And so what happens right here is that these materials are composites of this conchiolin, which acts as a tough protein, over here, and then the tablets are also they're made up of these hard materials that are sort of stacked up together in a layered manner, and then they're sandwiching a soft protein in the middle. And so the reason why this is very interesting for us engineers is because you have the ability to actually provide a lot of toughness and an increased mechanical performance overall for these types of materials. And again, because of the fact that you have protein layers in between crystal tablets, which act as a means for energy dissipation in these kind of materials, you get eventually this really increased toughness, which would be really, really beneficial for us, especially if we're looking into multi-material printing and things like that. And so the hypothesis that we made in our lab was that these types of hard, soft multi-materials, they will enhance the mechanical performance. And so before we can move on to talking about how we can 3D print these things in the lab, we can sort of make a hypothesis about, the fact that, if you do actually combine materials of, varying constitutive properties and then, arrange them in a certain manner, for example, right here we have layered configuration, we can achieve a much enhanced overall performance. For example, right here we're talking about force displacement. You can look at the area under the curve where you see for the brittle materials that you have, for the monolithic material, you'll have such a brittle response. And as if you move on to seeing what happens if you have a hard multi-material, then you get a slightly increase or some increase in terms of the toughness, but then you get a much more substantial increase in toughness if you look at hard, soft multi-materials. Okay? And so there's a lot of talking right here about hard, soft, hard multi-materials, but what we really sought after in this work was to see how we can numerically investigate fracture in these materials to better understand the toughening mechanisms that are involved in the response to fracture. And right here, I want you to pay attention to a lot of what we're talking about today about the interface, because again, this is something that's really important in these materials, because it actually will determine how your materials actually behave overall. And so there's going to be a little bit of math right here, so bear with me. And the last couple of presentations didn't really have that much math, so I'm kind of making up for that right here. So what we have right here is a model that we've talked about or we've worked on, which is basically called phase field. So if you're not familiar with this, it's a sort of continuum-based model that looks at fracture in a macroscopic manner. And what we do right here is, if we look at, for example, at a bar, it has a sharp crack in the middle. What we want to do in these types of models is we want to regularize that sharp crack topology, so kind of looking from what you have right here on the left to what you would have on the right. And so we go into a diffuse topology by sort of regularizing the sharp crack into a a region within the material, the specimen right here in this case, that has a finite length scale, which we call right here LC. And as that LC, the length scale goes to 0, you recover the sharp representation, and it's a pretty good way to look into fracture in kind of a diffuse representation. And so if you move on to dimensions, for example, just you go to multi-dimensional configurations right here. What we can see is we can quantify this damage or this phase field fracture variable by a variable that we call right here d. And this d will go from 0 to 1, 0 indicating no fracture and 1 indicating full fracture. And so we have this crack surface energy expression right here that is going to be a function of the critical energy release rate. And then if you go from the surface integral, which again would be the sharp crack topology, to a volume integral, which again now takes into account the entire contribution within the continuum, you get this integral right here, which is now going to be integrated over the entire volume. And so if we look at the total potential energy for this system, again, it's going to be written as a function of your usual terms right here, which you can see as a function of the strain energy, the crack surface energy, and the external energy, which is the applied load or applied forces. And then by using the variational principle, we can just subject this potential to a minimization with respect to U and D, being the displacement field and the phase field respectively. And then we can arrive at a solution for both fields. Now, the way that we account for the interface, which now is going to be the focus of the next couple of slides, is let's say that we have a domain, as you can see on the top right there, which is combined, or which is composed of two or multi regions of varying constitutive properties. And so in this case, I'm talking about hard, soft. So again, going from a small deformation to large deformation, which is going to be an important thing to consider for hard, soft multi-materials. For the region between the two materials, we'll have an interface. And that interface right there, what we did in this work was we modeled it using a CZM, or a cohesion zone model. And so right here, what we're doing is we're coupling basically the phase field that I talked about in the previous slides to a cohesive zone model by looking at this updated version of the crack surface energy, which now takes into account the bulk as well as the interface contributions. Okay, so far so good. And so for the interface, again, because that's the component that I added, I wish I had my pointer right here. Does this work for the pointers? No, but let me actually try to see if I can have my pointer real quick. Oh, perfect. Okay. Yeah, so this part right here of the interface, which now I added to my crack surface energy potential, you can see that I can now convert this into this expression right here, which takes into account this now going to be the delta U, which is the displacement jump at the interface. And so if you have an interface, you're going to have to find a way to calculate that displacement jump at the interface between the two materials, and you multiply that by the traction forces that are happening at the interface, right? And so now the updated total potential energy of the system will be the same as what you saw from before, but the difference now is going to be this additional component right here that I added for the interface, which again can be modeled using a simple CZM approach. In this case, it's not so simple because I'm working with the PPR, the PPR constitutive framework, which was developed by Park, Paulino, and Roser. And this was used because it is potential-based, and potential-based CZMs are actually, they've been shown to be much, to represent a much more physical representation of the interface rather than the displacement effective based methods, which sometimes can be incomplete. And so in this case, again, you have your typical traction separation law, which can take this form right here. And so if you implement that by taking the derivative of this potential base function with respect to the two displacement jump components, you will get your normal traction force as well as the tangential traction force. And then that is exactly what goes into this expression right here. You multiply by the displacement jump, and then you get your total energy potential for the surface energy for the interface. Now, this is all great, right? So what we did right here, we also did a lot of experimental characterizations, which I'll show in later slides. And then this is exactly to get these quantities right here, as you can see. So GC int means the critical energy release rate with respect to the interface in the tangential as well as the normal directions. And so we can actually run experimental tests to get those values for some of the modeling simulations I'll show in the next couple of slides. And we can do the same thing for the traction forces in the normal and tangential. So we can run we can conduct experiments to measure those two properties. So this is all something that we can actually work with because we can find these properties just using experimental testing on the various materials that we want to look at. And so I implemented that framework that you saw on the previous slide in an abacus. So if you're familiar with how that's done usually, we write a UEL, a user element subroutine. And so I wrote the code in a user element subroutine and implemented an abacus, and I wanted to test it for a couple of cases right here. And so right here I have case one, which consists of a hard bilayer composite. Right here you have an interface now perpendicular to the initial notch. The second case was looking at a similar problem, but now the interface is, or the interface is slanted with respect to the initial notch by some angle. And the third and fourth cases now consider the incorporation of the soft layer, right? Just because I talked a lot about the hard or soft multi-materials, and so here we want to see if we can push, if we can really if we can simulate these hard soft materials by actually looking at the large deformation component as well. And so again, here we have this sandwiched soft layer in the middle by two harder materials on either side of the inner layer. And now right here we just have a usual fiber reinforced composite. And so this can be the fiber reinforced concrete that people have talked about in the presentations earlier. And so looking now at this initial or first case, linear elastic fracture mechanics shows that we have two predominant crack growth mechanisms in these kinds of materials. And so we'll have crack deflection or crack penetration for these types of problems. So deflection means that the crack will deflect along the interface, as you can see over here, so on either direction of the interface. Penetration means you actually poke right through the interface and go into the second material and actually break the material in two, right? This is not what we want to have in a design that we make. And so if we're able to actually simulate this, it would give us a lot of insight about how to actually go into design for the future and for how to deal with that. And so LEFM says that if the degree to which penetration happens over deflection, right? These two mechanisms, it'll depend on this ratio right here, which is the interface critical energy release rate to that of the bulk material. So the ratio between the energy release rate for the interface to that of the bulk material, and this alpha parameter right here, which kind of quantifies the degree of similarity between the two materials, A and B. Okay, so if you're anywhere on the top right here, you're going to have a case of penetration. If you're down here, you're going to have a case of deflection, right? And so we can choose material parameters or properties that will land on either side of this space right here, and we can run a simulation and see if we can recover or get the response that LEFM actually predicts. And so that's exactly what I did for the case of penetration. We sort of made a model. We discretized the finite element mesh. Can put the interface as zero thickness elements in here in the middle, and then anywhere else we'll just have bulk plane strain 4-node quadrilateral elements. And as I said, we can choose material properties that would typically land us on the penetration space, right? And we can run model and see if that actually is, if we can recover that. And lo and behold, we get exactly that kind of behavior. As you can see right here, we ran the simulation. You can see we have a case of penetration right through the interface, which is what you would expect to see from LEFM, right? So that's all good. Now, for the case of crack deflection, we can do the same thing, but now just going down to the deflection case. And again, you can see that we have exactly that deflection as you can see, you expect to see from LEFM, and then just the crack deflects along the interface. And we can look at, what happens if we compare the force displacement plots for these two scenarios, and you can see that we have much lower peak force for the penetration, as you would expect, again, because it's not something that you would want to have, because you really break the material in two. And so again, we're able to see that very well here. Now, if we move on to the case of the crack impingement on an inclined interface, again, we can insert our zero thickness elements at the region over here, and then we can also look at what LEFM predicts for these types of composites. And again, you have this ratio for the crack for the fractional energy of the interface with that of the bulk material, as a function of the theta angle, which again is that angle that the interface makes with the initial notch. And again, you have penetration up here, but you have deflection down here. And we can do the same thing, so we can choose material properties for the penetration case and for the deflection case. For example, here I'm showing both cases. And you get the code or the model is able to actually predict very well what the LEFM theory actually says. So you can see right here we have deflection along the interface for the case where we pick these material properties, and we have penetration for the case where we have selected this material properties over here. And so that's again all great reinforcement for the fact that the code actually works. We can see what happens again if we just look at the deformed shape, and then again you can see very well that the code works very well. Now, I want to move quickly to the case where you have the hard-soft composite. Right here again, as I said before, we can run the mechanical property. We can run experiments to get the material properties, and then we can run on simulations. And what we see is we can now see that we have a case for penetration through the first layer. But then once the crack reaches the inner layer or the soft layer, it just skips it entirely, as you can see over here, and it just pops right out on this other side of the material. And you can see for the force displacement plot, you get this really nice first peak, followed by a much more hardening post the initial peak, and therefore giving us this desired toughness that we talked about in the very first slide. We also looked at what happens if we vary the thickness for the soft layer in the middle. And you can see right here, by varying the thickness of the soft layer from 7.5 millimeters all the way down to 0.15, we get the exact same response almost, indicating that you actually don't really need that much soft layer in the middle. And you can do very well just by looking at small values of the interface, of the soft layer. And then right here, we're just looking at an example for what happens if we run stimulation for the composite material as well as for the monolithic material. And again, you get this really interesting response that you would typically see in an experiment. Lastly, for the case of the fiber reinforced composite, we showed that the framework can do very well again in terms of predicting the fracture pattern for these types of composites. And again, right here, this is something that the literature agrees on, where you have the angle at which the separation occurs is at 64 degrees. And again, we get this really nice representation, meaning that the fracture phase field model works very well with the cohesive zone component. And I'll leave you guys with this slide right here for the conclusions. So I'm not going to talk too much about what I just did. But again, if you have questions, I'd be really happy to talk to you after talk right now or sometime during the day today. And so with that, I open the floor for questions, and thank you again for your attention.